Chapter 17 is all about electrochemistry, and we want to start off with a little bit of review of the ideas of redox. So electrochemistry is any chemical reaction that involves electrical current, so the flow of electrons. So we are dealing with some sort of chemical reaction where you have some sort of substance, atoms, molecules, where they're ions, whatever it is, where the electrons are going to leave that reactant and move to a different reactant. So there's going to be a flow of electrons. And so there are plenty of ways that these reactions look, but in particular, if you have spontaneous reactions, we're seeing again, where the electrons would flow spontaneously due to the chemistry, we can use that for something functional, namely things like batteries. So electrochemistry has a huge application in things like batteries and other sort of power sources that we use all the time. And so the underlying chemical reactions are called oxidation-reduction reactions, which are also for short called redox. So it's the reduction and oxidation. Generally, there is a lot of energy released in these. So they're really commonly used in practical purposes because they also tend to be very, very spontaneous. So there's the aforementioned batteries that we've talked about. There are also things like bleach. Runs based on electrochemistry. Things like burning stuff is a redox reaction. So a lot of very useful reactions because they tend to be very spontaneous. They really happen. Kinetics are also really low barriers usually. And so as a result, they're pretty useful reactions to get to go. Also, things like rust, corrosion in general. There's plenty of redox reactions that we really try hard to not happen. We know these involve the transfer of electrons. And so redox reactions always involve the transfer of electrons. And so that's where we kind of think about that as two steps. And that's where this kind of two-word name comes from. That oxidation is the losing of electrons and reduction is the gaining of electrons. So we think about the transfer as your first molecule or reactant losing an electron. That is the oxidation half of the process. And then the reduction is the other reactant gaining the electron. So you have kind of two halves to the process that both have to happen. And so when you're dealing with the transfer of electrons, the electron has to come from somewhere and it has to go to somewhere. So reduction and oxidation always have to happen in tandem. They always happen at the same time. There's never where you just have reduction happening because, reduction would be a gain of electrons. Where does the electron come from, right? It has to come from somewhere. It has to come from the loss from something else or the oxidation of something else. So these always happen at the same time. When we're looking at reactions, we want to start kind of working at the idea of characterizing a redox reaction. So sometimes when we look at chemical reactions, we can kind of clearly see that there's a flow of electrons. We could classify it as a redox reaction. For example, zinc solid reacting with copper 2 cations to make zinc cations and copper solid, right? We're changing what the cations are. Or if we have elements combining to form an ionic compound, that's very clearly the exchange of electrons, whereas a lot of redox reactions aren't going to necessarily be so clear. Something like a combustion reaction where propane is burning with oxygen, or, in this case where it's hydrogen peroxide reacting with itself, it's not necessarily as obvious that these are reactions where there is a transfer of electrons. We want to come up with a way to identify and to characterize this flow of electrons. To accomplish this, we define what are called oxidation numbers, which describe something like the distribution of electrons in a molecule. So the reason why the top reactions were more straightforward to see the flow of electrons is because we could recognize that charges were changing. So the idea of oxidation numbers is to create something along the lines of a charge description or a description of the charge distribution. And changes in oxidation number across a reaction indicate a redox reaction. So we're going to use these to characterize where are the electrons kind of in the reactants, in the products, and how can we see rearrangements or kind of more specifically transfers. And so we can then also define reduction as a decrease in oxidation number and oxidation as an increase in oxidation number. So these are the definitions where the language actually comes from. It's really confusing, the idea that reduction is gaining electron. Those two words seem oxymoronic. And so this is really where it comes from, that oxidation is a process where you increase the oxidation number, which comes from losing negative charge in the electron. So to determine oxidation number, we have some rules. It's basically kind of just, you go process of elimination. You look for things like elements, then you look for things like ions, because, if something has a charge already, we know elements have to be neutral. Ions just have their charge. We use those, and then we kind of back everything out. The most important rule is that the sum of oxidation numbers in a compound must equal the total charge. In the same way that if you have a neutral compound, all the charges on the ions have to be neutral. The same is going to hold true for the oxidation number for the sum of the oxidation numbers for each atom type in your reactants and products. So let's look at some examples. Determining oxidation number for each atom type. And again, for any particular molecule, each atom type is going to have an oxidation number. So F2, if I want to start with that, fluorine. This is one that does trip people up quite a bit because fluorine is a special case, but this is elemental. F2, this is fluorine. This molecule is just fluorine atoms. That's an elemental species. So fluorine in this case is 0. Only in molecules does fluorine get assigned that -1 charge. Next thing we have is CO2. So I want to look, carbon and oxygen each need them. It's not elemental, it's not ionic. So then I come down to my preferences. Well, oxygen is going to be given a -2. Oxygen always wants to be -2. So now the question becomes, what is carbon? And this is where I use the fact that the sum must be the total charge, where this is a neutral molecule, carbon dioxide. So the sum of all of the oxidation numbers must be 0. So if I think about that mathematically, basically what I'm saying is the carbon charge plus 2 times -2, that oxygen charge must be 0. So basically each oxygen atom is -2, and then I have 2 of those oxygen atoms. So then that'd be -4. Overall, my carbon must have a charge of +4. So the oxidation number of oxygen is -2 and carbon is +4. If I now look at sodium carbonate, this is an ionic species. So I can say right off the bat, sodium is a monoatomic ion, right? This is Na+ and CO3 2-. This sodium is then going to have an oxidation number of +1. Because the ion has a charge of +1, we'll just use that. So now I need to look at carbon and oxygen. That's a polyatomic ion, so I can't assign the charge from the overall ion to that. Instead, I need to use the rules I've used previously, that the oxygen is going to be -2 in this case. It has a higher preference than the carbon. So then when I'm looking to do the sum, now I'm looking for the sum of this carbonate ion. I have carbon and oxygen in there, and together the charge is -2. So when I look at the carbon and oxygens together, that sum needs to be -2. So this -2 matches this charge. This 3 oxygens comes from right here. And then I can see that I also then have a carbon from right there. And so -6 plus what equals -2? The carbon is +4 in this carbonate ion that we have right here. And actually, carbon is +4 in all carbonate ions, right? That didn't depend on the sodium, that just was from the carbonate. If we now look at P4O10, oxygen must be -2 here. Phosphorus doesn't have a preference. Total sum must be 0. So phosphorus times 4 plus 10 times the -2 has to be equal to 0, which means the phosphorus is +5, right? 4 times +5 is +20. 10 times -2 is -20. So you can have oxidation numbers, whatever you want them to be. They just need to be balanced out. Your charge sum up to that total charge. Okay, first video down. We're looking for questions on participation 331 due Tuesday, March 31st. None in this first video, but more to go, obviously. Midweek homework, we'll cover this first set of videos. And then for lab on campus, we got the chapter 15 and 16 participation quiz. We'll meet at 11 a.m. in the classroom. We'll do that. And then we'll do redox titrations. Do you want to note redox titrations is a topic that we will talk about in the second set of videos this week. So in the pre-lab and the stuff, I am assuming that you don't know many details about redox titration, but it's an application about balancing, which is a topic from this set of videos. So the pre-lab will be about a lot of that kind of background information, and then you'll see it in lab on Wednesday, and then hopefully the videos will make a lot of sense because you've actually done redox titration. If you have any questions about anything, let me know. Otherwise, welcome to the set of videos. I'll see you in the next one.